Hello and welcome to the first Pytorch tutorial in this series, the Pytorch Basics tutorial. So hopefully you've gone through the introduction, you know a bit about what we're doing here. As I said in that tutorial, we're starting at section 2 of our series. So again, you can find all of these notebooks in the GitHub repo. I'll put a link in the description. Starting that section 2, Pytorch Basics. If there's interest, I can go over the other sections, but there is an assumption going into this video that you are familiar with the content in those two previous sections. If there's interest, I can make a video going over it. Even if you are familiar with Python and even NumPy, I recommend just briefly going through it to make sure that you are sort of familiar with all that content, because I am sort of expecting that you are, and I'll refer to it as well. So this initial notebook is going to be split into 3 videos so that I can sort of cover each part adequately, so you can sort of skip videos if you want to go over them again. So in section 2, you'll find this notebook under Notebooks and Tutorial 1, Pytorch Basics. Another thing I wanted to touch on quickly is that this series, we're focusing on the implementation of a lot of deep learning, machine learning concepts in Pytorch. And so while I will cover some of the concepts at some level, a lot of it is sort of expected, or I won't go into too much detail about it. However, I have provided or will provide a bunch of resources that you can use to sort of either jot your memory or learn from scratch. So this deep learning Google Sheets link here will take you to this Google Sheets. If there's any information that I haven't covered in these external resources, or you have some resources that you think I should add, just let me know and I'll add those. As you can see, we've got a whole bunch of YouTube series, we've got free deep learning books, a whole bunch of articles, blogs, videos, and some other Pytorch tutorials that I'll add a bit more to that as well, which got the official tutorials here as well. So I'll link the relevant sections in the relevant notebooks as we go further in the series, so you can see exactly what I'm talking about and maybe get some additional background on those. But for this video, we're really just going through the basic functionality of Pytorch. And as I said, I'll be relating it a lot back to NumPy and the functionality of that, because there is a lot of similarities between the two. So what is Pytorch and why do we need it? So Pytorch is a deep learning library, a deep learning framework, really, that enables us to implement complicated, potentially very large deep learning models, and we'll go into what deep learning means later on. But it introduces a lot of functionality that is sort of required for deep learning, or that makes implementing deep learning models and training deep learning models a lot easier. We'll see things like defining models, optimizers, loss functions, and importantly, the autograd or auto differentiation capabilities of Pytorch that a lot of other frameworks have too, but Pytorch is a very popular one. And it has a bunch of additional tools as well around data sets, data processing, pre-processing, and things like that. And also, if we want to train our deep learning models on a GPU, we have the functionality there in Pytorch. So the 2 main modules, at least for now, that you need to install are Torch and Torch Vision. So Torch is the sort of main neural networks or deep learning submodule of Pytorch. It contains a lot of our machine learning functionality or functions. So torch.nn, the submodule there, the neural network submodule, contains a lot of our optimizers, our loss functions, our models, and our layers, as we'll see later on. Torch Vision contains a lot of computer vision algorithms, and it's where we have our data sets, our data loaders, and a lot of pre-processing is contained in that library. We won't look at it too much in this section, but we will go in depth later on. Okay, let's jump into Pytorch now. So as I sort of covered in the NumPy tutorial, we could sort of define matrices or vectors as lists, or matrices as list of lists, and you could create your own functions to perform matrix operations, but there's a huge array of libraries, or most commonly NumPy, that allows us to do a whole bunch of operations on arrays and vectors, and we create instead of a list of lists, we create an object called a numpy array, right? And that can be any sort of dimensional array. And we can initialize that with lists or list of lists. And there's a whole bunch of other functions like ones that will automatically create our arrays. And we can use numpy built functions like matrix multiplications and a whole other array of functions to perform the sort of matrix operations or tensor operations that we would, expect to want to use in data science and in machine learning. So I'll go into more detail about that in the NumPy section, but I just wanted to show that Pytorch has a lot of the same functionality, and you can bring that knowledge from NumPy into Pytorch. It's kind of by design that they are very similar. So we can also initialize our torch tensor. So it's not a NumPy array, it's now a torch tensor. We can initialize that with a list of lists. We can specify the data type of the resulting tensor. So here we are defining it explicitly as a float tensor, 32-bit float tensor. If we were to just simply initialize it with torch.tensor, which is, I think you see pretty commonly, it will sort of assume or try and work out what the resulting tensor type should be from the original data. So W here, you can see we have floats, so it's going to use a float type tensor. So it's resulting in a float tensor. If you were to use X, which is just ints only, you can see it's imported it or converted it as a long tensor or an integer type tensor. So if you want to explicitly ensure you've got one type or the other, you can do that with float.tensor, or you can also just convert to float or long like that. But we'll see that in more detail as well. Again, we have tensor operations, matrix multiplication, and as we'll see, a lot of the functionality with in place addition, subtraction, division is all the same. So we can convert between NumPy arrays and tensors and back. So you can initialize a torch tensor with a NumPy array, which is what we've done here, and we can convert from a torch tensor to a NumPy array. So all those other libraries, modules that exist for operating on or that expect a NumPy array, we can use with the outputs of our model, or we can use in Pytorch by converting that torch tensor into a NumPy array and then convert back. That does sort of break the autograd functionality though, but we won't worry about that for now. Okay, let's go straight into some more Pytorch operations. So like I said, a lot of the operations are pretty much identical. A lot of the functions are the same. They might be named slightly different things or might be located in different submodules of Torch. But if you can kind of think of it in NumPy, it probably exists in Pytorch. Pytorch kind of breaks down some functions into sort of a set of functions that we sort of use very often. We'll see that in a moment, what I'm going on about. But for now, we can initialize tensors randomly. There's a whole set of ways to randomly initialize Pytorch tensors, very common in deep learning. I think it's a bit more expansive than in NumPy. But here you can see we just used a uniform distribution between 0 and 1. And we can just do things like element-wise operations, multiply by 10, add powers. So these are all element-wise operations, not matrix operations. Again, very much the same as NumPy. So some tensor operations that are a bit different. So like we saw, you can do matrix multiplications with 2D tensors. But in Pytorch, we sort of introduce or use a lot of what are called batched operations. So we use batches, and we'll get into that in more detail later on. But a batched operation you can think of as, maybe we've got two matrices and we want to do a matrix multiplication on them. That's fine. We can use matmul or some other matrix operation. But let's say we've got 10 pairs of matrices. So we have two matrices, let's say we have 10 pairs of them, and we want to multiply each of those matrices together independently. In this case, we've got two pairs of three 3x3 matrices. So we've got pairs of three 3x3 matrices. You can think of this 3D tensor as three 3x3 matrices, for example, where this first dimension here is what you could call the batch dimension, right? So what if we wanted to multiply these pairs of three 3x3 matrices together and get, as a result, three 3x3 matrices, right? This is very useful if we want to perform, if it was just three of these pairs of matrices, it might not be much, but like I said, if it's 10 or 100, again, very common in deep learning, as we'll see, to perform huge numbers of matrix multiplications in parallel. We can do or use these batched operations, which sort of really become powerful once we move on to GPUs, and these operations can really be performed in parallel, right? So instead of performing these matrix multiplications one by one sequentially, we can do 10, 100, 1,000 of these operations at the same time by utilizing our GPU with these batched operations. So again, if we were just to add tensors together, again, it's an element-wise operation. It sort of behaves as you'd expect. But you can see that with our batch multiplication, we again get a 3x3x3, where you can think of each of these 3x3 matrices here is the result of the 3x3 matrix multiplication of those pairs of matrices. Hopefully that makes sense. So some other operations, transpose. So hopefully you're familiar with maybe transposing a 2D matrix, kind of rotating our matrix there. You can do that as well in Torch. So if I was to define a 2D tensor, we can transpose it. It's a bit different to numpy, which is just dot capital T. I think we'll transpose it for you. Dot T brackets will transpose a 2D tensor. Again, it needs to be a 2D tensor or you'll get an error. Pytorch will get angry at you. Right, it needs to be less than or equal to 2 dimensions. But we can do transposing with high dimensional tensors. Again, it's a little bit more complicated, right? So if we want to transpose, we're going to swap 2 dimensions, which is what we're doing in transpose. It's a little bit more complicated. And again, I don't really have a good explanation for what we're doing here on an intuitive level. To sort of get an intuitive understanding, it really helps to sort of look at the original tensor and see where the values have gone and sort of trace them back. We don't do a huge amount of transposing higher dimensional tensors, though when we do, having the context can be a bit helpful to understand what's actually going on. But for now, just pointing out that we can do the transpose of higher order tensors, just like we can with numpy arrays. So indexing, another very important concept that hopefully you are familiar with. Indexing, again, we're just selecting chunks, individual values or chunks out of a larger tensor that we might want to perform operations on. So it performs, we use indexing exactly the same way as in a numpy array. You can say index with -1, which gives you the last, or you can do negative indexing, so -1, -2, whatever, indexing from the end, just like in numpy or even in lists, Python lists. Right, so we have our original tensor. We're going to index the last element of dimension 0, so we should get a 3x1x4 tensor. So you can think of this 4D tensor as two 3x1x4 tensors, and then you can think of those 3x1x4s as three 1x4 matrices, whatever helps you sort of conceptualize it. But in this case, we're indexing the last index of dimension 0. So think of that as index 0 of dimension 0, and this one as index 1 of dimension 0. So indexing this one, which is what we get returned here. We can provide more indices. So index 0 of dimension 0, index 1 of dimension 1. So that's index 0 of dimension 0 gives us this, and then index 1 of dimension 1 gives us this. So we get a 2D result here. That should give us a 1/4. It does. And then we can provide as many indices as we want. If we don't provide the index, just like in numpy, it will assume we want all of it. So we'll assume we've put like a colon there. So that's for all of the values in that dimension. So all of dimension 0 in this case, and then index 1, 0, 2. So all of dimension 0, you can think of all of these values in dimension 0. And then we want, for all of this, we want index 1 of the second one. So that's this and this. And then 0, that's the first one. This. Oh, nope. All of this. And then it's index 0, which is this first one. There's only one index there. And then it's index 2, which is this one. But again, it's for both of them. So again, all of this, index 1 to this and this, index 0 because there's only one, so it's still just this, and then index 2 again for both, so it's this and this, which is what we get as a result. Again, if you're not familiar with that intuitively, playing around with it like this can help you build that intuition. It's a very important thing, indexing, and we use it a lot. So hopefully you have a good understanding of it. If you don't, playing around with it can help. So describing tensors, another important thing. So what different characteristics can our tensors have, such as the shape, the number of elements, and the number of dimensions. So shape just gives us basically the size of each of the dimensions. So we have a 3x5x3x2 size tensor. Dot size does the same thing as dot shape, unlike numpy. Numl gives us the number of elements, the number of values contained in our tensor. You can see it's 90. You can get that just by multiplying each of these. 3 times 5 by 3 times 2 is 90 values. And ndim gives us the number of dimensions of our tensor. We have a 4D tensor here. 4D, again, if you're unfamiliar with the dimensionality of our arrays or our tensors, the dimensionality just refers to the number of indices that we need to provide to access a single value within that tensor. So I kind of skipped over that, but hopefully you have a good understanding of that. If it's a 4-dimensional tensor, it means we need to provide 4 indices to access a single value of that tensor. Right. Don't need that. Oop. Reshaping is another very important operation. In data science, if you're playing around with any data, reshaping is really important. Again, very important in machine learning. It is a thing that can be difficult to understand intuitively, especially when we're reshaping these high-dimensional tensors. Understanding where everything kind of goes after the reshaping can be a bit tricky to understand. One way that is kind of might help understand how things get reshaped and moved around that I find students like is, imagine you've got your original tensor and you sort of flatten it out into a single long vector, and then we sort of repack it into our original shape. How you'd sort of do that flattening out is by basically going through each of the values in order. So by flattening it out, we're basically having it in the way in which Pytorch actually stores this in memory. Pytorch, even though it might be a 4 or 5 dimensional tensor, in memory it's sort of stored as a long list. So you can imagine this flattening out working by going through each of the values in order. So in order basically means we start at sort of very first index you can think as 0, 0, 0, 0 for our 4D one. And then we go 0, 0, 0, 0, 1, and 1, and then 1, 0, and so on, until we sort of flatten it all out. So we start with 0, 0, 0, 0, 1, we go up until the max size of that dimension, and then we move on to the next one and the next one. And if we do that, we sort of get this flattened out tensor here. And if we were to now reshape it into, say, a 3 by 30, what we're doing is Again, we start with index 0, and then we need 30 values. So what we do is we take the first 30 values of this, which goes up to here, and we chuck that in the first dimension here. And then we have the next index of the first dimension, and we need the next 30 values, which are this value to wherever it is, the next value, the next 30, and then that's the next chunk here, and then the final chunk here. We do the same thing. Works the same with higher dimensional tensors. If it was a 3-dimensional tensor, you can think of the first index, and then of the first dimension, then the first index, the next one, and then say if it was size 3 in the final dimension, we take the first 3, and then if we want to take the next 3, the next 3, and stack it up that way. So again, playing around with it, thinking about it as this sort of flattening and then reshaping may help you build an intuitive understanding. Another thing we need to make sure is that the shape of the tensor we're trying to reshape it to has the same number of elements as the original tensor. So here, 3 by 30, that's 90 elements, the same as our original tensor. We can also use -1 to as a don't care dimension. So if I define the first dimension size 10 and the next one -1, I'm saying I don't really care what the next dimension is. It's going to be 2-dimensional. I don't really care what the size is, as long as the size of the first dimension is 10. Again, the size of that dimension needs to be a multiple of 90, or the other way around. Basically, Pytorch needs to be able to actually pick a value here such that it gives us 90 values. So if you divide 90 by 10, 90 by the first dimension, the next value needs to be a whole number, right? It can't be float. You'll get an error. Yeah, hopefully that makes sense. So I kind of said that some of the operations or reshaping or functions in numpy kind of been split into separate functions in Pytorch because of how often we use them. An example of that is squeezing and unsqueezing, adding empty dimensions. NumPy does have sort of an equivalent expand dims, which sort of does the same thing, and that is to add an empty dimension. I kind of talked about the batched operations before. It's very common in Pytorch. A lot of the functions we use expect that first dimension to be the batch dimension. Even if we only have one data point, it may expect a batch dimension, so we need to add that and potentially remove the empty dimensions. And because we do that so often, we've got these dedicated functions called squeezing and unsqueezing, which do just that. Just to clarify what I mean by an empty dimension, an empty dimension I refer to as an empty dimension is any dimension where we have an index or a dimension of size 1. So call it empty because if it only has a single index, a single possible index, then we can kind of ignore that index. So if we have a 3-dimensional tensor, but one of those is empty, size 1, then we only really need to provide 2 values because that empty dimension, size 1, is always going to have the same index. It's always going to have the same index. We can just assume it's index 0 and then just worry about the other 2. So think of it as an empty. We don't really need to provide an index conceptually, even though we do need to when we actually implement it. So let's look at unsqueeze. So unsqueeze is adding that empty dimension. And what we do is we specify the dimension that we want to add that empty dimension to. Note that it needs to be the index we provide to add that empty dimension needs to be equal to or plus 1 of the actual size. So let me try that again. If I want to add an empty dimension to a 2D tensor, I can either add it to the 0th index, the 1th index, or the 2nd to 3rd index, right? I can't unsqueeze 3 to a 2D tensor because we're adding more dimensions that actually exist. So this first example here, we've got a 2D tensor, I'm unsqueezing 2, I'm adding it to the end. If I was to unsqueeze 3, we're going to get an error because we don't have that index 2 or dimension 2 yet. You need to unsqueeze 2, then unsqueeze 3. Hopefully that makes sense. Right, so we can either add it to the end or we can add it to either of the other dimensions. So dimension 0, dimension 1. Here we're adding a dimension 1. You can see we kind of put that empty dimension between the 3 and the 2. So we've shifted them out. Most commonly though, what we're doing is adding it to index 0, which is the empty dimension, adding that batch dimension. So squeeze is the opposite to unsqueeze. If we have a tensor with some empty dimensions, again, it's just a dimension with size 1, we can unsqueeze by specifying the specific dimension that has the empty dimension. The dimension that we specify for squeeze needs to be size 1, an empty dimension. If we specify another dimension, it'll give us an error. If we don't specify any index for squeeze, it will remove all the empty dimensions. Be a bit careful with that. Unless you really know that it'll be okay to sort of just squeeze at all dimensions, you can have situations where, for example, if you have a batch dimension, if you're processing batches and you've got this 5D tensor, but it's got empty dimensions in it, you squeeze and get rid of those ones. If you ever come across the case where my batch is now 1 value and I accidentally squeezed all of the empty dimensions, well, I'm going to squeeze out that batch dimension, and maybe later on I actually still need that batch dimension, but I didn't think of the case where the batch size could be 1. So be careful about not specifying. That's just good coding practice, really. Specifying the exact index that you want to squeeze is more useful, right? Stops mistakes being made. It's a very common mistake I've seen a lot of. Broadcasting. So in this section, I'm not going into broadcasting in much detail. However, it is an incredibly important concept for you to understand. Hopefully you have some idea about it. A lot of languages like MATLAB or NumPy do broadcasting, do broadcasting. It's a very important functionality that you should know in some detail, right? Again, just an overview. Broadcasting allows us to do either in-place operations like addition for tensors that are different shapes, and they will broadcast across those empty dimensions. I go into a lot more detail in the NumPy tutorial. I have a whole section on broadcasting and some examples there. I'm just showing that it also happens in Pytorch. So if you're not familiar with this, definitely go over that NumPy tutorial and familiarize yourself with that. And there's also an example of why broadcasting is important and why it's useful. Again, sort of a batched operation that helps us speed up a lot of examples in the k-means clustering tutorial or example code in the NumPy section. Again, we give a sort of hard example of why broadcasting is so useful. It stops us from having to do so many nested loops. That's one example. So we can speed up our operations a lot by doing broadcasting. And again, when we start utilizing our GPU, that's going to be so much more important. So I'm going to leave this video here. I'm going to leave Pytorch AutoGrad and more advanced concepts in Pytorch to a later video. So hopefully you followed that. Again, it was very basic, this first video, just seeing some of the basic operations of Pytorch. Next videos, we're going to get into some more interesting, more unique things about Pytorch, and I hope I'll see you there.